Okay. Right, so welcome everyone to this week's One World IAMP Mathematical Physics Seminar. It's my great pleasure this week to introduce Christian Hainzl. So his talk on correlation energy of the electron gas in the mean field regime. Before we go ahead, I just want to say that this talk is going to be recorded and will be available on our YouTube channel. We'll also have information in the chat for people who are looking at it online about our organization and the seminar series. So if you're here for the first time, you can also join our mailing list and follow our seminars in the future. So now, without further ado, Christian, the floor is yours.
Okay, thanks a lot. Thanks a lot for inviting me to give a talk here. So I will talk about the correlation energy of the electron gas, and in particular what is in the literature known as random phase approximation. So now I have to emphasize that this is a joint work with Martin Christiansen and Phan Nam. And in particular, yesterday we had the defense of Martin Christiansen, who really had a major contribution to what I am talking here. So he's just newly doctor, and hopefully he will stay for some time in Munich. So now let me start. So first of all, I want to talk only about the quantum aspect of a system which is basically known since the 30s as something which is called the Jellium. So you can think of Jellium is used to model the electronic behavior in metals. So you can basically think of a piece of metal, and of course you might, if you be precise, you might think of basically positively charged ions here located at the lattice and electrons running around. So a little bit, if you simplify the model a little bit, then you basically smear out the positively charged part. So you think of a basically smeared background, and in this background, electrons running around and interacting via the Coulomb potential. So in a more simplified form, I describe here the Hamilton like that, where you have n electrons, where the kinetic energy is described simply by minus Laplace. So for the physicists, we use, of course, units where h bar is 1, where the electric charge is 1, and where the mass is 1/2. So, and since the electrons are basically in the background of a uniformly charged part, in order to basically make sense of this Hamiltonian for, let's say, in a thermodynamic limit, we subtract the contribution of the background. And doing that, and of course, we use the fermionic Fock space such that electrons are described by anti-symmetric particles. And one of the first mathematically major results in this direction was actually the establishment of the thermodynamic limit, namely, if you take the ground state energy and calculate the thermodynamic limit, where you basically fix the density and then go either with n or with the volume to infinity, then it was a result by Lieb and Naunhofer in 75 that this thermodynamic limit exists. And this is actually a highly non-trivial statement, because in particular of the long range of the Coulomb. I mean, this was a result which was established after the famous paper of Lieb and Leibowitz from beginning of the 70s, or where they established the thermodynamic limit for molecular systems. Okay, so if you want, so first of all, that is a statement about the thermodynamic limit, but of course, you can ask, can we give a little bit more quantitative, can we describe that in a little bit better quantitative way? And basically, since the beginning of the, since the start of quantum mechanics, one way to describe many particle systems is by so-called Hartree-Fock theory, where you look at particles which are at individual particles which are non-correlated, which are for fermionic particles described via Slater determinants. Now, so one thing which one can describe is now the Hartree-Fock energy, which you get by taking the Hamiltonian, restricting it to states which are described by Slater determinants. And then, of course, you can also take the thermodynamic limit. Now, let's say the best statement about the ground state energy of Jellium, or the most accurate statement for the ground state of Jellium and the thermodynamic limit up to today, is a theorem of Graf and Solovay. I think it was published in '94, but I think that maybe the statement is from '93, but it doesn't matter. It is actually based on an correlation inequality, which was developed by Volker Bach a few years earlier. And it basically says that the energy of the Jellium is to leading order described by the Hartree-Fock energy plus lower order. Now, so rho again is the density, and we look at the large density behavior as you would expect the behavior in metals. And what is the interesting part here is that the Hartree-Fock energy, as already shown in Graf and Solovay, is to leading order given by this part. Now, the first part simply comes from the interaction of, let's say, the non-interacting Fermi sea. So if you would take, basically, if you go to Fourier space and take your Slater determinant by particles which are just inside of the Fermi sea, where that basically corresponds to rho 1/3, and this is basically the Fermi momentum. If you take that as a trial state, then you get for the kinetic energy this term rho to the 5/3, and for the exchange term you get rho to the 4/3. So basically already here you see that the leading order of the Hartree-Fock is given simply by the ground state of the non-interacting Fermi gas. Now I want to basically mention a paper from 2018 of together with David Gontier and Mathieu Levin, where we actually showed that if you compare the energy which you have here of the free Fermi gas with the real minimizer over Slater determinants, where you really, you see here, you basically take care of the interaction of the Coulomb interactions. So you minimize really over Slater determinants. Then the difference, if you would take simply the energy of plane waves and the real ground state, is actually only exponentially small in the density. So in other words, the Hartree-Fock energy is basically given by, you can say you take the free Fermi sea, you plug in Hn, and what you get here is as good as if you would minimize over all possible Slater determinants. So that just, okay, but now, so this is the best result so far. Now the question is, what can we do to go beyond? So what I want to talk about is that we so far did not manage to do it exactly in this problem, but in a slightly simplified model. So, but first of all, now I talked about what do we know from a mathematical perspective, but of course from a physical perspective, one already studied this problem in the 30s, and of course, from a physicist's point of view, what is the question? How can you describe the correlation energy? Was solved many years ago, but of course not in a mathematically rigorous way. So just let me review a little bit the history. So I think the problem was posed maybe in the 30s by Wigner. I'm here not so sure, but he was one of the first who treated this problem. And he also realized that it's not so easy to go beyond Hartree-Fock. Namely, it was realized soon that there are some problems, in particular, that second order perturbation theory does actually fail. And so Wigner realized that in the 30s, and actually in 36, there was a paper of Bardeen who argued that if you use the Hartree-Fock calculation, then it is insufficient to compare with experiments. In particular, the specific heat of metals or the cohesive energy was really off by was really off from experiments if you really only calculated by Hartree-Fock approximation, and therefore it was clear that one has to do something to go beyond. Now, after that, there were some phenomenological theories, basically also by Wigner, by somehow extrapolating some results which suggested what the correlation energy should be. But the first microscopic derivation actually, from a physical point of view, was given by Bohm and Hainzl in the 50s. So I actually also mentioned here a paper by Heisenberg from 47, which I find interesting, because there he also, he showed by explicit calculation that the perturbation theory fails. But the interesting thing about that paper is he called it death theory of superconductivity. And he argued, end of the 40s, that basically the reason that second order perturbation theory fails has something to do with superconductivity. But that just as a side remark. So in the 50s, Bohm and Hainzl had 4 papers where they considered this problem of electrons in a metal. And what they actually did, so first of all, there are 4 papers, 2 of them are classical, 2 of them are quantum. The last one is from Hainzl alone, but maybe the third one is in that sense the most interesting one, because he treated the quantum case. And what they did, they started from an Hamiltonian, and then they somehow separated the contribution. So they decomposed the Hamiltonian into a contribution which which describes collective electrons, a collective electron behavior, which they call plasmons. And this collective electron behavior is really specific for the Coulomb potential. And maybe I will argue at the end of the talk why this is the case. So they decomposed this collective part with the individual electrons. And then they calculated the energy of the collective electrons, and these individual electrons, which were also moving within the plasmons, they only saw each other with a screen Coulomb, and then they could use second order perturbation theory here. So they were the first ones then to come up with a correlation energy, which they stated behaved like rho log rho. So so they basically got one term correct. Now, after that, Gell-Mann and Brueckner, by a different method, really established the formula, so they described the correlation energy. So again, the correlation energy is the difference between the ground state energy and the Hartree-Fock energy. And they basically gave 2 terms, one which depended on rho log rho and one just on rho, and they really calculated this constant. So they did that. The approach is kind of interesting. So they did that by doing a formal resummation of Feynman diagrams. So maybe let me just for those who actually know that, let me just go tell you a little bit more about that. So if you can graphically represent use perturbation theory. So here, what you see here is the energy of the kinetic energy of the free Fermi gas. So the next order here is just the first order perturbation theory. So this is something, if you take the free Fermi sea and calculate this one, then what you get, of course, is the direct energy and the exchange term. The direct energy here is basically subtracted by the background, so that does not really appear. So this is here the exchange term. Now you also can write the interaction between two particles, the interaction like that you have an incoming electrons with momentum p and one in q. So you interact. So the scattering amplitude is given by v hat of k, and then you have here p minus k and q plus k. So you have conservation of momentum, and then how do you? So basically two parts. So you can think of, you have the Fermi sea, two particles here, one with momentum p, one with momentum q. They interact with each other. They jump outside and then they fall back in again. And there are two ways to fall back in, into the same part or in the other part. So into the same part, this gives this term, which basically is cancelled by the background. And then if you basically jump out and fall into the other one, then this is called the exchange part. So that you get if you would basically combine these two. So in the exchange part, maybe let me also write it like that for Coulomb. For Coulomb in the thermodynamic limit, you can describe that by 1 over p minus q squared, and you integrate over p smaller than kf and q smaller than kf. So this is of the order of kf to the 4 or rho to the 4/3. Of course, then it is basically negative. So this is the first order perturbation theory. And now let me also say something about the second order. The second order, of course, you would get by taking this Fermi sea, then 1 over the kinetic energy minus this W0 E psi Fs, and that corresponds graphically here, that basically here you interact again. And then you again have the choice, either you combine it here or you combine it here. And one gives this part, this diagram, and one gives that diagram. So if you combine it like here, then you get, let me just do that, then you get something where you have a p here, a p minus k here, and then you interact and you have the same with q and q plus k. So now that is now the second order, and you can go on, you have any order. So what Gell-Mann and Brueckner basically realized, they said that the idea of Pines can be, and Pines, Bohm and Pines can be translated like that you basically need only sum up a particular kind of diagrams, namely the ones which I have written here, namely those where you only have these bubbles. So only these bubbles interact with each other. What do these bubbles mean? So if you look at that, you create basically out of the Fermi sea two momenta p and q. They jump out, they interact, jump out, they interact again, and they jump in again. So therefore, you have a particle p, and then you basically have a hole with momentum p minus k. So what this graphical thing here suggests is that you have a pair one particle in the whole, which basically interacts with other pairs. So from this picture, you can guess that you only have pairs and they interact with each other. And the other one, which is important, is this one. So, and that is what I will also tell you at the end, because that was basically also what the main idea of how to do it then rigorously is, that you basically think that the main contribution comes from the interaction of pairs. Okay, so that was Gell-Mann Brueckner, and what one has to say, that if you really look at the thermodynamic limit, then the interesting thing is that all of these diagrams, they diverge, so they're infinite. All of these diagrams give an infinite number. But as what was realized by Gell-Mann and Brueckner is that if you sum up these diagrams in a kind of a geometric series, then suddenly you get something which is finite and makes sense. So that was the idea of Gell-Mann and Brueckner. And the interesting part is that they interpreted the random phase approximation so that a pair of particles are interacting with each other. So now this idea then basically was put into a Hamiltonian formalism by Zawada, and by Zawada, Brueckner, Fukuda, and Prout, also shortly after Gell-Mann and Brueckner, where they actually wrote down a Hamiltonian in such a way that in this Hamiltonian they threw everything away except the interaction of pairs. Pairs with one momentum inside and one momentum outside of the Fermi sea. And that is here what one can call a bosonization approach. And this will also the main idea in what I want to tell you. Okay, so this approach by Zawada, where they really do a kind of bosonization, he was able to really get the first term again, but he didn't get this term correct, because in this approach, what was described here by this diagram was not included. So by this one. Okay, but I will come back to that later. Now, let's be a little bit more precise. Now, what is now our goal? We are not able to study the full problem of Jellium. We look at a little bit simplified model. So what do we simplify first? We are not considering the thermodynamic limit. We take a box, let's say a box of side length 2 pi. Well, the 2 pi is chosen by convenience, because then in momentum space, the conjugate momenta are just given by C3. So we look at the box and we look at the mean field regime. What do I mean with the mean field regime? Well, we take here basically the Coulomb interaction, but we divide it by 1 over kf. So we keep the number of particles, and for mathematical convenience, we take the number of n so that it exactly is the number of points in the Fermi ball with radius kf. So basically you take you take here the kf, you take the Fermi ball, then you have the lattice here inside, and n of kf is just the number of points here inside. Okay, so and of course, since we're on the torus, the potential here, it should be mimic the Coulomb potential on the torus. So basically we take the Fourier transform 1 over k square, and we take here we sum over k. And we leave out the k equal to 0, because this corresponds to subtracting the background. So now this is the model, and for this model, we want to say something about the correlation energy. Now, in this model, of course, n is proportional to rho, well modulo the 2 pi here. So we can, instead of thinking of rho to infinity, you can think of n, or you can think of kf, because the relation between the Fermi momentum and the number of particles is just that. Okay, so if you do that, of course, the ground state energy now behaves like n to the 5/3 as before, and the exchange energy, so what we had before, so you see the exchange term, which was written here, was given by k to the 4/3. If we do a mean field approximation, we have to multiply by 1/kf. So what we get is a kf to the 3. So we can actually write here that the kinetic energy, so that is kf to the 5 plus something, or actually minus kf to the 3. That is due to the mean field approach. So now, and now again, or even more, what is true, that if you look at the Hartree-Fock ground state, so if you minimize overall possible slated determinants under the constraint that the number of particles is n, this is again given by just taking the expectation value of the Fs of the free Fermi sea, so of the which only consists of the plane waves. So basically, you take all the points here inside, take an e to the kx, and do the slated determinant. That to leading order gives the ground state energy, and actually the error is really exponentially small in n. Okay, so now what do we expect from the correlation energy in the mean field regime? So if we take the Gell-Mann Brueckner formula and ask what is the corresponding thing for this system where we really are on the box of side lengths to pi, and in the mean field regime, then we just take, so what we do here, we just take the integrals actually, which are not found by Gell-Mann and Brueckner, but by Savada and others, and then what is here denoted as conjecture is that the correlation energy corresponds to this bosonic correlation energy, which corresponds to the sum over the bubbles. Yeah, so this is the first term. So this is an explicit term where the f is here given by logarithm 1 plus x minus x. Now, this v hat of k, you can think of 1/k square, as I said, as Coulomb. Now, this just describes the mean field approach, and that is basically a particular integral where the behavior goes like kf log kf. So you see for the Gell-Mann Brueckner, we had the rho log rho. So the rho is kf to the 3, but since we are in the mean field regime, you are 1/kf square smaller. So now let me write that again. So the HF behaves like kf to the 5, then the exchange energy is kf to the 3, and now here for the next ones you are at 2 orders lower, namely you have to kf log kf, and the log is kind of the log is here interesting, and the exchange term, this is given by this term, and this is proportional to kf. Now you might ask, what is this lambda kp? That is given here by p square minus p minus k square, and that actually is the effective energy of, you can say, one of these pairs. So I will come back to that, but if you wonder what this lambda kp is, this is basically the effective kinetic energy of such a pair. Now, so if you want how, so this term, so if you write down exactly what it is in Coulomb, so this actually, if you combine that, maybe I erase that. So this is this goes like k dot p plus q minus k. And here we have 1 over k squared and 1 over 1 over p plus q minus k squared. So now if you take this term here and take the first order, so you see from the log, you expand the log, you subtract the x, what you have as the next order is minus 1/2 x squared. If you do that, you basically get a term which looks like where you have 1 over k squared times 1 over k squared. So this is basically 1 over k4 and 1 over p plus q minus k times k. So I just write that here. Maybe I come back to that because so since we are on the box, this term here is finite, but if you would do a thermodynamic limit, then you would get exactly this first, second order bubble diagram, which go to which would diverge. But I want to emphasize that the term which is written here, when you sum over all these diagrams, this is finite, not only on the box, but even in the thermodynamic limit. So this would make sense also without the mean field and in the thermodynamic limit. So now so now our main result, which I'm talking about here, is together with Martin Christiansen and NAM, our recent result is really to give a rigorous upper bound to this conjecture of which you can extrapolate from Gell-Mann and Brueckner. So we actually prove that we write down an explicit trial state, and I will explain how this trial state comes about. And we show that you really have here smaller equals, so you really have here a basically precise estimate. And if you wonder how the error term here look like basically we get actually log kf, square root of log kf, which is much better than this part. So we actually get a pretty precise upper bound. So now, of course, this is now, as I said, the interaction was for Coulomb. We had mean field, we are on the box. This result, so a similar result for more regular potentials was, so basically this was studied within the last few years, in particular for more regular potentials V, starting in particular for potentials where the Fourier transform has finite support. And there was the first two papers. One gives an upper bound for this system, one a lower bound. Basically two nice papers by Benedicta, Nam, Porter, Schlein, and Seiringer. So if the V hat is finite, then, and you also look at the mean field approximation, so you also have here a 1 over kf, then one can show that the energy is also to leading order given by the Hartree-Fock energy, and one has this correlation, this bosonic correlation term, which corresponds to this, basically can also be described by this term here. I mean, the specifics here are not so important. But there is a difference, namely, if V hat is regular, then you don't see the log. So you only see the log for the Coulomb. And this behaves like kf. And then the next important thing is that the exchange correlation, which was for Coulomb important because you see the kf and the kf log kf are not really distinguishable. I mean, you have to basically see that as a term belonging together. In the case where you have a more regular potential, this actually, in this specific case, the exchange correlation actually goes like 1 over kf, so it is much smaller than this part. Now, the lower bound in this paper was proven for a small constant here in front, for a small enough constant, and then in two other papers, namely together with Martin Christiansen and NAM, we established basically a different method. So it's actually based on different ideas. The main overall idea that you use basically bosonization method is the same, but the approach is differently. And actually within, there were two papers within 1 or 2 weeks who established to extend it, this proof to potentials which are no longer finite support, which just have which just satisfy this this relation. Okay, so for that actually, so now I want to describe what are the main ideas of our approach, and so both approaches were in kind somehow inspired by Zavada, who really used a bosonization picture that you only think of bosons. We basically made them a little bit finer such that we also could tackle the exchange correlation. And this is the main thing of this paper. So maybe I forgot something, namely if you add here a lambda, and you also think of basically what is the next order for small lambda, then there was actually a previous paper by myself with Marcello Porta and Felix Rexe when we were in Tübingen altogether from 2018, where we basically made a rigorous approach of perturbation theory. But the main idea, so the big step towards the Gell-Mann Brueckner was then done in these papers. Okay, so now let me be more precise. What do we do exactly, and how does this bosonization work? So now I come to describe what is the main, what are the main ideas. So formulated in momentum space, I write the Hamiltonian like that. So you basically describe the interaction here by means of momentum variables. Now, so what we have in mind is the picture of Zavada. We want to describe pairs. So how can we rewrite this thing in pairs? So first of all, we can basically swap. First of all, we can put the P here inside. So we commute this through, and then what you basically get then here instead is something which I can write as rho of k. This is the Fourier transform of the density operator, rho k minus n. The n comes from doing the commutator between that, and what is the rho of k? So the rho of k is basically the sum over p, a star p minus k, a of p. Okay, so now if we rewrite it like that, and then we look at this part, and what we want to think about, so the idea is that we want to get the correlation energy. So we want to calculate everything relative to the energy of the Fermi ball. So, and the idea is that this is basically done by somehow pairs of particles where one particle is inside and one outside of the Fermi sea. So if you now separate this part in parts where the P is outside of the Fermi sea and the P minus K is inside of the Fermi sea, so you can do it, let's say, outside, inside. So actually, let me just go here for a second. So I described here the rho of k. Now here I use the dagger instead of the star. So what you can do, you can just separate this in a sum where the P is outside of the Fermi sea, so bigger than kf, and P minus K is inside of the Fermi sea, plus the other way around, the P is inside of the Fermi sea, the P minus K is outside of the Fermi sea, plus terms which come from inside and outside. So in a concise way, I can write it like that. Then the idea is that if Savada is right, then basically these two parts should play the main role. Now that's why we then rewrite the interaction simply using these parts. So now, sorry, let's go back here again. So now we decomposed the row of K, and what we got now is then an interaction which looked like that. And what we also managed, we could basically pull out the energy, basically the Hartree-Fock energy, so the expectation energy of the Fermi sea. Now, and then the kinetic energy, of course, now we rewrote by just subtracting the kinetic energy of the free Fermi sea, which is just the sum over the p squares. Okay, so now we are left with this part, and now the next thing is basically, so I just wrote here error, but of course one has to prove that this is an error. And first I want to present the idea that how can we describe this really as, in which sense is this bosonic? So, and now this piece is as we had before, is a sum over this BKP, which describes, so A star P basically creates a particle inside the Fermi sea. In particular, if you think of acting of psi fs, then A of P basically annihilates a particle outside, and that creates a particle inside. But the Fermi sea we can think of filled. So basically that is zero, because the Fermi sea is yeah. So you have to consider the vacuum. The vacuum is basically the Fermi state. So this corresponds to a pair, and let me maybe describe it here again. So what is this pair? You have a momentum here outside of the Fermi sea, and P minus K. This is then, you can think of a hole inside of the Fermi sea. So this is basically the pair, and what we denoted as Lun as LK, this is just this part. Of course, you have to think of that this sits on this lattice, but I just described it in a continuous way. Okay, so now what rests is to justify that can be in some approximation seen as a something quadratic in basically pairs of particles which we want to treat as bosonic. So therefore I just want to describe here. So now we have these pairs, and then if you think of the pairs where the P is outside of the Fermi sea, P minus K is from inside. If you ask what are the commutators, then this actually commute. And if you calculate this one, then of course, if they would be real bosons, if this pair of fermions would be real bosons, then this would be zero. So if this would be zero, they would be real bosons, but they are fermions, so they are not. So you have basically an error term like that. But now, so the idea is, so first of all, if you act with this part on the field Fermi sea, then you see this A of P is outside. So basically then you get zero, because the particles are only inside the Fermi sea. And if you act with A star of P minus K on this state, then you also get zero, because they're all filled. So on the Fermi sea, acting on the free Fermi sea, this is actually zero. So you could expect that if you are close to the ground state and you don't have so many excitations around the Fermi sea, that you can consider this as almost bosons, and that is actually the main idea. So you can even make it more precise, so that the part which is here, you can basically estimate it by the number of excitations. Number of excitations means the NE. The NE is you count how many particles are created outside of the Fermi sea, which is the same as how many holes are created, because the total number is fixed. So now the idea is that close to the ground state, the expectation value, the number of excitations should be much smaller than basically, let's say, kf square, which is essentially the number of points in the loop. So then, if this is the case, then if you would here sum over all p and q, then this part is of much lower order than the part comes from here, and you can consider it as fermions. And actually, for our trial state, which we have, we actually for a trial state we get that the number of excitations is of order 1. Okay, so now doing that, we now get an idea of an effective Hamiltonian where the interaction is here described by something which we consider almost as bosons. And there is, of course, still the kinetic energy. So this part is already quadratic in the B's. Now, what about the kinetic operator? And now the interesting thing is, if you take this kinetic operator and commute with, let's say, B star, K and P with this pair, then you get here lambda Kp times B star Kp. So you get here the energy of the pair. And this is the same. So assume now you would have this BKPs would be real bosons. Then this term you would also get by just taking this kinetic energy. If you would take this kinetic energy, if you commute with a B star, so you would get rid of that, and the only thing what stays is that. So basically, the kinetic energy behaves as if it looks like that. Of course, so the difference is non-zero, but still we can now replace the kinetic energy by this part, which is also quadratic in this piece. So now the idea is, now we just take that, and if the B's would be bosons, then one could use a Bogolubov transformation to really diagonalize this part. And diagonalizing this part basically gives the exchange part of the bosons, the exchange correlation. Now so taking this idea for the upper bound, we just define a trial state, namely e to the k and fs, where that is the free Fermi state, and decay is just so that E minus K H effective E of K, that if the B's would be bosons, then this would be really diagonalized. So you would have the energy of the correlation energy bosons plus something which behaves like B star P, like an excitation Hamiltonian. And of course, this part here on the Fs is 0. So what you basically get as an upper bound is first of all this one, and then how can one see the correlation energy? Well, for the exchange energy, for that we really use that the B's are not bosons. So in some let's say in some short way, I just don't want to say much about that. So if you basically diagonalize this, then if that would be bosons, then you would have really basically the correlation energy, but for this part. But since these B's are not bosons, when you take the commutator here, then you get the term which also includes the part which distinguishes the commutator of the B's from real bosons. Namely, if they would be real bosons, you would have that, and that is just the error term. And in order to get this exchange correlation, you have to use this error term. So you have to plug that in, calculate, and then you get the term out, which is basically exactly this exchange contribution. Okay, so I don't want to say more about that. So now, as I said, so for the main result which I presented before was one got by an explicit upper bound, where you use a trial state. And actually also the results I stated before for the regular potential, where we really basically not only have an upper bound, but we really have a statement that about the correlation energy, and we get this bosonic correlation expression is based on the same idea, using exactly some kernel such that this unitary, this is a unitary because of the -1. This basically diagonalizes essentially this Hamiltonian, and one has to basically get upper and lower bounds with this idea. Now, as I mentioned at the beginning, so the first result in 2021, where we considered an interaction, a more regular interaction, we actually not only described the ground state, but we also had a kind of an operator estimate. And this operator estimate allowed us also to say something about the excitation spectrum. And here is the point where the plasmons come in. So I want to explain to you what, when the physicists talk about plasmons, that can be described by basically an eigenvalue of a particular matrix, which appears here when you diagonalize this Hamiltonian. Then you get the Hartree-Fock energy, the bosonic correlation energy. As I said already before, in this case, if you have this assumption, then the exchange correlation is unimportant, is of low order, and what you get is an additional excitation term. I don't want to say more about that. So the statement here says if we take here basically restrict here to some sectors, basically to some sectors or charge sectors or sectors for how many excitations you have out of the Fermi sea, then if M is 1, then you can think of elementary excitations. So basically, then you basically have think of what happens if you have one excitation, then this term cancels, and then you only have to look at the part coming from here. And the statement is that although you see here still a quadratic Hamiltonian, that for M equal 1, the spectrum of this part is really described by the spectrum of a matrix. This is basically the statement, and the spectrum of this matrix can be written down explicitly. And the spectrum of this matrix, so this is now my last slide, the spectrum of this matrix, so the eigenvalues of this matrix are given by this lambda kp. So as I remind you, this was this p square minus p minus k square. So this is this interaction energy of a pair, which is created out of a Fermi sea, so a pair, an electron and a hole. So the energy is either given by that, or one gets an integral equation, which is an equation for this epsilon. So, and here comes, so here I wanted to just explain that why the plasmons only play a role for Coulomb potential. So if you replace, if you put in here Coulomb 1 over k square, so if you put here 1 over k square, 1 over k square, and if you don't consider mean field, so you get rid of this, now this term cancels that term. So this term cancels that term. And if you then say, for simplicity, because you don't like sums, look at the thermodynamic limit, then you basically get an equation like that. And if you look at this equation, the interesting thing is, if you think of k equal to 0, so you get rid of that and you get rid of that, then there is a solution for epsilon, because you simply have now to integrate the p over the Fermi sea. This gives the number of particles. And when you solve for this epsilon, then you basically, to leading order, get that, where the little n is basically the number of particles. So then you get here an eigenvalue which corresponds to this picture. So, and then of course, this is for k equals 0. So this here is an implicit equation. You can calculate how does this behave, this epsilon of k, and you basically get here something which behaves here quadratically. And this is called the plasmon mode. So this is actually way over the ground state eigenvalue. So this is for small here so here this is basically an eigenstate which is pretty stable. And I just want to mention that if v of k does not behave like the long range Coulomb 1 over k square, then of course this thing here does not really give this branch, but would lie lower. Also, if you look at the mean field, then this would be basically much lower. So that I just wanted to tell you where this plasma comes from. Of course, we only proved equality for regular potentials, but if you then take the leap and put in here Coulomb, then you see the plasmon. Okay, so that's now the end of my talk, and I just say thanks for those who stayed and listened. Yeah.
Thank you very much, Chris, for the very nice talk. I now leave the floor to the audience for questions. So actually, I think I have one naive one. So this exchange correlation energy that you were mentioning, how did it look like diagrammatically? I think I missed it.
No, the exchange is this.
Okay.
So, and this you can really, you get by basically asking what is if you combine that, then you have the restriction that q plus k is equal to p. So you can say k is so now, sorry, this is not really correct, because you have to have this other one. So okay, forget what I said, but diagrammatically it is really this one.
It's just one diagram, that one.
It's just one diagram, and only one diagram contributes. But mathematically, of course, you can isolate this one diagram, but it is not so easy to prove that all the rest is of lower order.
Okay, and that was, you said it was missed in the earlier works?
In Savada, or the bosonization idea, which also basically, which also you followed, when you do a Hamiltonian, then only these diagrams are really treated. And Savada himself added this part by hand, and then argued that when he does that, he gets the same as Gell-Mann Brueckner.
Okay. Thank you. Questions or comments?
Gell-Mann,
yes,
Gell-Mann,
go ahead.
Gell-Mann and Brueckner. So which diagrams they included?
No, that's all this here. diagrams. So from the I did here, if you look here at these third order diagrams, then they included this one and all the others where you only have the interaction of bubbles with other bubbles. So they included all these diagrams and summed over these diagrams and argued that if you sum over these diagrams, you get the finite expression.
Yeah. What is the difference between Sawada and Gell-Mann and Brueckner in terms of a prediction? Do these two approaches give different numbers?
Yes, because Sawada only takes this one.
Yeah, but you mentioned that Sawada could add.
No, by hand. No, by hand. He said he gets an energy which he got by diagonalizing an explicit Hamiltonian. So he diagonalized the Hamiltonian and he got the number which comes from these things. And then he said that, but what is missed is the fact that there is one term which is non-bosonic in some sense, and this is this one. So he added that by hand, and then he argued if you add that, then you go to Gell-Mann and Brueckner.
Yeah, so can one say that Gell-Mann and Brueckner is better than Sawada?
Yes, but we are arguing you can improve Sawada by also including by doing it more precisely and also extracting the correlation, this term.
Yeah, so Hainzl and others is better than both Sawada and Gell-Mann and Brueckner. Is it correct?
We gave an upper bound. Well, I don't know what it means better than Gell-Mann and Brueckner. So let me go here again. So what we did, so basically Sawada treated this Hamiltonian as if the B's were bosons. So then he got the bubbles. So we took this trial state where this K would be so as if that would be bosons, then we plugged in and we also extracted not only the bosonic part, but also the exchange correlation, which you can do by simply then again taking into account that these are not bosons. Then basically also so treating terms which come from the non-bosonic behavior. So in that sense, this is for an upper bound better for this particular mean field model because we get an explicit description of the ground state, and it is a closed form, and we don't have infinities. Of course, you can say Gell-Mann Brueckner would say, well, you have to do that in the thermodynamic limit and so on. But I think as a step into a more rigorous mathematical part, it is a kind of step. And also, this is, I mean, it's not only about proving the ground state energy, it's also about getting an idea what is meant under this random phase approximation. Of course, you know random phases, but it ends up to be exactly the same idea.
And can your approach be explained purely diagrammatically? I mean, that's that you sum up this class of diagrams and.
No, yeah. I mean, you see, you can do that. You can do that. You can actually then say that you look at the trial state E of k and then the free Fermi C, and then H you see as an approximation. You can write here H E F, and then you write here E k psi F S, and then this is that e to the minus k H F e to the k psi F S, and then you look at that, and if you then basically do an infinite Duhamel formula, you would get an infinite series of diagrams. And you would see that all the diagrams which are included in Gell-Mann and Brueckner are also there if you basically go on like that. So in that sense, this is included. And you also get the exchange contribution by just taking into account that you have a term which is not bosonic.
Thank you.
Thank you. Other questions or comments? Does not seem to be the case. So let's thank Chris again for the very nice talk. Thank you, Christian.